Okay, let us continue with the last topic this morning. Next speaker is Nicola Gigli from CISA, and he will speak about concepts in hyperbolic functional analysis. I'm very interested in this because perhaps it's possible, so I would like to know if it's possible or not.
Thank you, man. So I have 50 minutes starting from now, right? Yeah. I got this recorded. So, so thanks a lot. Thanks a lot for the invitation, Esther, for putting this up. And it's really a pleasure to be part of this community and this meeting. Among other things, it also gave me the opportunity to visit Esther for the first time. You have a lovely hometown. I'm enjoying it very, very much. So my talk, yes, I'm going to speak about this hyperbolic functional analysis. There will be a few theorems in my talk, so and maybe just a few definitions. So basically, what I want to convey is that something that might be called hyperbolic functional analysis is worth exploring, and maybe in the exploration we could find something which is interesting. Yeah, so let me. So the first part of the talk, I will just try to motivate why. I mean, isn't there enough functional analysis already? Or why should we speak about something in this direction? Then I will introduce some, the main concepts that are behind this theory, which is really being built now. So it's I don't think that those concepts that we discuss today will be the last concepts in the field, but perhaps hopefully the first, if the theory really flourishes, and then I will go some definition. Yeah, let me start. Motivation. I will every now and then when we want to introduce a new concept, maybe I will refer to a previously existing one. So in my view, Banach spaces, those that we know about, those are elliptic Banach spaces. So you will see something that maybe we want to call hyperbolic Banach spaces later on. And whenever we make this sort of comparison, I will draw the elliptic field, elliptic concepts on the red on top, and the hyperbolic ones in blue on the bottom. I often do this joke that saying, in Lorentzian signature there is something negative. When something is negative, it's below zero, so it's below, and below zero is cold, so I give it a cold column. Whereas above zero is certainly warm, so it's on top and with a warm column. All right. So let's start with something easy. We know RD and we know the Euclidean distance and all. So pick a finite dimensional vector space D. A Euclidean scalar plot is just a symmetric form of signature plus plus plus. Obviously, it is non-negative. Obviously, we can take square root of GVD for any vector of V, and that's a norm. Now, G being non-degenerate means that it induces a norm, still a symmetric scalar plot with the same signature on the dual. So we do also have a dual norm on the dual of V. And we do have the Cauchy-Schwarz inequality. And Cauchy-Schwarz inequality implies two very well-known inequalities, or facts. One is that we do have triangular inequality, and the other one is that this dual norm satisfies and has a variational representation. Okay, and I'm pointing this out just to highlight the trigger fact that once we have this, you can state this without having a scalar plot in advance. So in fact, we define norms by just saying things satisfying triangular inequality and dual norms as in this. Now in the Lorentzian setting, what does it work? I pick a form of signature, so I will choose a different sign convention from the one of Andrea, but it doesn't really matter, it just simplifies a bit my presentation. So it's a form of signature plus minus minus minus. And I consider so we have we have this picture that Andrea kindly erased, but it was not. So we are in saying Minkowski, and one of the two branches of the cone, we call it the future cone. Okay, so we don't care about what happens in the past, I just care about what happens in the future. And in this future cone, where GVD is non-negative, I can do square root of GVD, and that's the norm or Minkowskian norm of it. Okay. Now again, G is non-degenerate, so again it induces a dual norm on the dual of V. And there is a dual, there's a very standard notion of the dual of a positive cone, which is the set of linear functions that sends the positive vectors into positive reals. And it turns out that for every linear function in the future cone, G star of L is still non-negative. So I can take the square root. And it happens that for two vectors, both in the future cone, we do have the reverse Cauchy-Schwarz inequality. So in this Minkowskian signature, GVW is greater or equal than the normal V times the normal W. And this implies, that the opposite inequality that those we are used to are in place. So we do the reverse triangle inequality if both the vectors are future, and the dual norm has this, variational characterization in terms of inf of the action on vectors with normal twist. All right. So if that's very, quickly said, roughly said, we know what is Banach space theory. Banach space theory is basically you pick these two axioms, you add the Cauchy completeness, and that's in essence what Banach spaces are. And the question that I want to pose is, so is there anything in here? So what is the natural, infinite dimensional, counterpart, complete counterpart of Minkowski space? So is there anything in it? And so that's by the way, so maybe I want to add something. These are the only two signatures for which you have these triangle inequalities and variational characterizations. So it's an easy exercise to check that you have, say, a form which has at least a plus on, say, RD, and then in a neighborhood of a vector where GVB is positive, you have the classical triangle inequality, then the form is Euclidean. If on a neighborhood you have the reverse triangle inequality, then the form is Lorentzian. So no other option is in place. So don't expect to have another theory for plus minus minus. Okay. Now, of course, why should we care? I mean, we lived happily so far without just with Banach spaces without this Lorentzian counterpart. And for me, the motivation is basically what Andrea has been discussed. Part of what Andrea discussed in his talk, and it comes from smooth geometry. So there is this curvature dimension condition by Lostrom-Bellamy that builds up on works of many people, McCann, Ottolani, Stumborness, McCann, Clark, etc. So, but so Lostrom-Bellamy distilled what the CDKN condition, encoding rich curvature bounds on metric measure spaces. Now, one property of this of the condition is that it encodes even Finsler-like structures. Finsler manifold may satisfy curvature dimension condition, which could be good or bad depending on your point of view, but surely it is interesting to know whether there is an analogous theory that just basically focuses on the Riemannian counterpart. And it turns out this theory do exist. What you have to add to Lostrom-Bellamy condition is this condition of infinitesimal invertiality that I introduced a few years later. Now, the story of infinitesimal invertiality is, if possible, even longer than the one of the curvature dimension condition. Namely, one should start from the intuitions about of de Giorgi about the possibility of developing a gradient flow theory in purely metric spaces. Then should add the seminal intuition by Jordan, Kinderer, and Otto that tells that basically the heat flow is the gradient flow of the relative entropy with respect to the Bastian distance. Now, Lostrom-Bellamy basically defined curvature dimension as saying, the entropy is convex with respect to the Bastian distance. So, seems like a good idea to try to look to study the gradient flow of this convex functional in this Bastian space, and that was my starting point. Then further elaboration with Kubada-Dota, and then Ambrosio-Savaret, finally this condition. Okay, so this is about I will not really tell too much, but it's about the shape of Sobolev functions on metric measure spaces. Basically, functionality comes a bit into play. Now, more recently, Andrea and Fabio defined the so-called time-lag curvature dimension condition. So this is, in a sense, precursor to the null energy condition that we discussed. So in a sense, you look at the convexity of entropies, and actually, he defined it already. So you look at convexity property of entropies along time-lag geodesics in the Bastian space. Again, this work McCann, Mondino Sur. It builds a lot on the works of Buseman, Penrose, more recently Kunzinger and Seeman in the axiomatization of what it is the Lorentz analog of a metric space, what sometimes is called metric space time, or Lorentz and space. But anyway, so it is a condition that it has the property that the smooth world it's equivalent to a suitable rich curvature lower bound on time-like direction. But it's synthetic, so it works in a non-smooth world. It has better stability properties. Okay? Now, as soon as this condition came out, one of the questions that people were asking was, okay, but is there an analog of infinitesimal invariant in this world? The question was a bit non-trivial because you don't have Sobolev functions in Minkowski are not really a thing. Okay, because GVV can be as a signature. So if you ask yourself what could be say the W12 norm of a C-infinity compactly supported function in Minkowski, you run into trouble because maybe the differential points in space-like directions, and then you don't cannot take the square. But anyway, so it turned out that this is possible. There is an educated guess of what this could be. This is a result of a big collaboration. We mentioned later on what the people, but the eight of us basically worked and tried to define and kind of Sobolev-like notions in this Lorentzian space-time setting, and single out of that a notion which wants to be the analog of this. But now, so regardless of what these precise things are, there is one thing that I want to sort of stress out, is that one of the reasons why the loss luminosity condition has been so successful, and why the analog of TCD condition by Carletti Mondino is being successfully studied, is that it builds up onto theory that we understand well. So these are, it has to do with optimal transport, and we know about optimal transport a lot. We know how optimal plans are made, duality relation, lifting, localization, you name it. We know how to work with optimal transport. And one of the reasons why infinitesimal Bertianity has been successful is that it builds up on function analysis. So which is also something that perhaps even better than optimal transport. So again, I will not go into details, but basically take any existent statement in the world of either CD or RCD spaces concerning differentiation operator. All of those existent statements rely on existence resulting function analysis. So the differential of a Sobolev function exists as an element of a certain Banach space. The Laplacian the same. Harmonic functions do exist because they minimize the energy on certain Sobolev space. The heat flow exists because there is a certain gradient flow theory, etc., etc., etc. So all the existences, so everything exists first and foremost because it exists in some Banach space or Hilbert space. So then the question is, what is this? Okay, so we are throwing so there should something which satisfy a kind of parallelogram identity on some structure which is Minkowskian-like, it's not really a vector space, something crazy. How can we make use of this? Okay, if you are a little bit familiar with the analysis in metric measure spaces, you can ask yourself the following question: where does the differential of a function belong, or what it is the differential of a function in the setting of non-smooth Lorentzian manifolds? Okay, the analogous question in the Riemannian signature, but maybe in the non-smooth world, has a number of different answers. Depends a little bit on which kind of axiom you put yourself in. I guess the first one to propose such a notion was Chigger, then Weaver, more or less at the same time. Later, myself, even more recently, Saltanis on Eriksson Bicke, together with Eriksson Bicke. But regardless of the specific, in each case, the differential of the Sobolev function is first and foremost an element of some Banach space. Okay, and here, we really don't have anything like that, because the triangular inequality goes in the other way, and that's what violates our first rule.
So when you say differential, are you differentiating in any direction or only like in
whatever? In fact, I tend to differentiate just in causal directions. So that's the kind of. But if you want, put it this way. So take the collection of smooth, compactly supported future vector field in Minkowski. Do this guy belong to some naturally defined complete space? The analogous question in RD would be, I could pick LP vector fields or subar vector fields or whatever they are here. But what about the Lorentzian signature? Where, of course, the first issue that we have is that even that we have reverse triangular inequality, Cauchy complete really makes no sense. Okay? So what? All right. So here are the key concepts. In the classical world, we do have. So this is my proposal. So that's the whole of my talk is here. So in the classical setting, we have vector spaces and triangular inequality. And what I propose, what I think is reasonable to do, is that we should replace vector spaces with what I'm calling wedges. So a wedge is just like a vector space, but you can only multiply by non-negative reals. So I would not work. I don't want to work with Minkowski. I just want to work with the future. That's the idea. And norm, rather being something that satisfies triangular inequality, should satisfy the reverse triangular inequality. And Cauchy completeness should be replaced with directed completeness. Directed completeness means that every directed set must have a supremum, and I will tell you in a second what is the partial order behind it. Okay. Now this notion is really crucial. So let me spend a little bit of time here, but I could quite literally spend the whole of my talk on this slide. So first things first. Even forget about no smooth geometry. Say you just study, Lorentzian manifolds, and one of the first questions that you want to answer to is, what does it mean that this manifold is complete? For a Riemannian manifold, we know. For a Lorentzian manifold, given that there is no, classically intended distance, you don't have Cauchy completeness, and you maybe have a hard time identifying whether you are in in which sense, say, Minkowski minus a point is not really a complete manifold. Okay. You could say, well, hold on a second, we have a geodesic that cannot be extended over there. Yes, but that happens even in black holes. So you want to distinguish, a problem that comes from, really some physically relevant condition from the problem that you just forgot to put a point where the point should be. Okay, and the typical, there are many, ways of understanding this, but a particularly successful one is the concept of global hyperbolicity. Shortly said, that is not entirely correct what I'm going to say, but shortly said is saying this: if you pick 2 points, one in the future of the other, and you pick the diamond in between them, so the set of points that are in the future of the first and in the past of the second, this guy is compact. And now you easily see that this identify this distinguishes Minkowski and Minkowski minus a point, because if your diamond does not contain that point, it's not good. Now problem is a compactness property is not really a completeness property. I mean, it should imply some sort of completeness, but this is too strong. If you want to go into an infinite dimensional theory, asking for local compactness is just too much. You need really to replace compactness with completeness. So if you want, this general paradigm in analysis and just in analysis, you want to trade regularity for compactness. That's something one typically does. But in order to do this, you really need to, in a sense, put yourself into a complete setting. Okay, once your base is complete, then you can hope that something nice. Okay, so we really need to give up any sort of compactness and replace it with some form of completeness. Now, why directed completeness? So why I'm asking. For instance, the existence just of directed suprema and none of both of directed suprema and the dual notion of filtered infima. So every filtered set, so directed set going down as an infimum. For instance, well, first of all, so a good this has to be so for this notion there is a nice working existence result. So for what concerns a completion procedure. So you having so with metric geometry metric geometry say we don't just know what is a complete metric space. We can also start from a metric space which is not complete and complete it by the usual procedure. Now, and this is something that we also do very often, say in functional analysis, we say, the software space, whatever is the closure of, the infinity functions with this or that. So we start from, some nice class of objects, and we complete it because we want to work with something complete. And this completion of a procedure is crucial. And it's crucial that you have, a good theory for that. And a good theory for that, for this only exists in some sense, as far as I can tell, only exists if you decide to complete, in some sense, monodirectionally, not bidirectionally. So there is an existence result even for two-sided completeness, but it's an ugly theorem. It's an ugly construction. Well, it's a good construction for direct completion. And what is directed completion? So maybe it is worth to spend 2 words on the following thing. So in matrix geometry, there is more rigidity that here in this Lorentzian or causal world, because if you have a metric space that embeds isometrically and densely in a complete metric space, then this complete metric space is the completion of the original. Now, with partial orders, it does not work this way. Let me give you an easy example. Imagine your partial order is, say, 0, 1 without 1. then in a very natural way, the completion is going to be IAD 1. Okay, that's it. But now if you have two copies of this without any relation between these two, you have at least two possible candidates for the completion. One is I add 1 point to this guy and 1 point to this guy, retaining the not relation. Or the other one is, I basically add the same point that does something like this. And in both cases, the embedding is dense in whatever, reasonable way you want to define it, and both target spaces are complete in the sense of directed completion. So how do we distinguish these two? Well, basically what you say is you select the best one in categorical terms. Is the concept of reflector. Let me quickly mention this. You have a partial order in here. You say that Y is the completion provided this guy that's isomorphic into Y and Y is complete. And for any other complete partial order set, and for any other map, sorry, I forgot to say one important thing. And for any other map T with the so-called monotone convergence property, I will mention in a second what this is, there is a unique map here that completes the diagram. And monotone convergence property is what is this? It does that basically. Respecting directed suprema. So a map between partial orders has the monotone directed property provided, in a naive way is that whenever you have an increasing sequence with the sup in the starting space, the image of the sup is the sup of the images. But you ask this not just for increasing sequences, but more generally for any directed set, just because it's technically more complicated. Okay. The name comes because in relevant applications, this will really be the polarity theorem, essentially, so the monotone convergence property theorem. Maps between partial orders, having just these properties have not been studied too much, as far as I can tell, except there is a community of people that back in the 60s they were studying semantics of computer languages, which I have no idea what it means. I'm just amazed that in the 60s people were studying something about semantic of computer languages, and for some reasons, morally speaking, an algorithm was more powerful than other if it was possible to compute it more. So this gives a kind of partial order between algorithms, and they were interested in this map of these properties, and they called this monotone property in their field is called the Scott continuous, because there is a certain topology you can put on partial orders for which these are precisely the continuous maps. I'm not calling this way because I'm not really putting any topology. That's an issue of the field if you want, but I still want to say that these guys were doing some serious mathematics from just the little bit that I can understand. One of the things that amused me is that they basically, by studying completion of continuous functions, basically they end up studying topology on lower semi-continuous functions and they find gamma convergent 10 years before the Georgian for same kind of reasons. So different application, but the idea was to have a compact house of topology on a good set of functions. Your dream would be the smooth function. The dream cannot be true. You go to lower semi-continuous, like a gamma convergent. That kind of. Okay. But anyway, so in some sense, maybe a crucial point maybe that I want to make is the following. If you believe me for a second that respecting directed suprema is a property that you would like to have for your maps, then two things are natural. First of all, it's natural to ask that directed suprema exists. And it is natural to ask that to define the directed completion as the completion for which has this universal code. And everything follows very natural once you realize that these MCP properties is a good thing. Okay? Now, one thing which turns out to be nice is that this construction of directed completion is compatible with at least the basic examples of spacetimes and future completion of spacetimes that you can find in general relativity. Now, if you don't know what it is, doesn't matter. If you know, then you know that you can draw Peros diagrams of spacetimes, and for instance, that would be the one of Minkowski, and then you want to complete the space-time, basically to see what happens far in the future. This notion is very crucial. Even the very definition of a black hole and event horizon has to do with future completion of space-time. And now I'm proposing a concept of completion that works in any partial order. It comes somehow, some way from general relativity and Lorentzian geometry, so it's natural to ponder, the relation between this kind of completion and known ones. And at least in basic structures, they produce the same thing. So if I take the directed completion of Minkowski, what I'm doing, I'm really adding a future null and future time infinity, and the same is Worship. So with Worship, the Kruskal extension, you get the two copies of future null infinity of Minkowski plus S2 cross R in the region R equals 0 inside the black hole. So exactly what you would expect, which I guess is nice. And last but not least, this kind of concept is strongly tied to no-smooth geometry. So of course, in complete metric spaces, we can work on them. We can study, among other things, Hyperbolic functions. And in fact, in this paper, Tobias Beran, Matthias Braun, Matteo Palisti, myself, Argal Monayan, Robert McCann, Felix Lotte, and Clement Seman is the one I was referring to before, where we define infinitesimal libertianity. And while we were studying, then there is a lot of interconnection between this paper and this kind of notion of directed completion and completeness. And because the point was the following: we were studying this, and a lot of duality between LP spaces for p smaller than 1, this already appeared in Andrea's talk, started to pop out. And of course, we have a very beautiful duality theory for LP spaces for p bigger than 1, but we had nothing, we had nothing for p smaller than 1. So I started, to study this topic and to investigate in which sense you could have some sort of completeness. And I came out with this notion, the existence result. So I said, well, maybe we can try to replace global hyperbolicity in this no-smooth setting with some sort of directed completion, tailored, not exactly this, but tailored to our setting, where there is also topology and other structure. And it turns out, so this is the paper where for the first time, the kind of directed completeness appeared in this setting of no-smooth Lorentzian geometry. And it turns out that the robust calculus can be did. So infinitesimal Minkowskianity we defined in this set. And more recently, this also has been played a role in a recent result for a compactness statement for sequences of spacetimes. So this is a stability result that Andrea, together with Clement Seman, proved. It's not the result that he mentioned. So this is more in the direction of a la Grom, there is the beautiful fundamental result by Grom on precompact. If you have a sequence of Riemannian manifold, uniform upper boundary emitter and dimension, and uniform lower boundary Ricci curvature, then at two subsequences you have a limit metric space of metric spaces. In your dreams, you would like to do the same for Lorentzian geometry. We are not there yet. The closest analog so far is this paper by Andrea and Clemens. I don't want to go too much in details, but basically one thing that they do is they out of curvature assumption, they start to cover the Lorentzian manifold, the spacetimes, with small things, so not both but diamonds, and now they're uniformly across the sequence. So basically out of this, they can extract a limit object, where the limit object is just a countable set with a little bit of structure, time separation, and so on and so forth. And now you have your countable set, and you maybe for instance to realize whether this countable set is a dense subset, say, for instance, of a smooth guy, or maybe you would like to know, maybe you change a little bit your covering, you would like to realize that the limit guy is unique. So it's the same as the one you had before, and for all the reason you need a completion procedure. So and they revert to something along this line. Technically speaking, is a bit different. Again, there is more structure in this case, but the bottom line is that there is a nice existent result for one-sided monotone and complete. Okay. So that's about the kind of notion of completion that I want to discuss. Now, what about why wedges? Why not just vector spaces? I mean, Minkowski after all is a vector space, and moreover, we had function analysis built over the concept of vector space. So I should really give some reason for why I'm giving this up. And the first and most important reason is that in applications, morphisms, so linear maps with MCP, they easily take the value plus infinity. They really tend to do this. And once you have a linear map that takes the value plus infinity, you say, I don't know, L of V is plus infinity, L of W is, say, minus infinity, And now good luck at trying, to understand what is or should be L of B plus W. Huh? While if you have just a one-sided sort of thing, then, no issue appears. I already mentioned that the confusion process only works well if monodirectional. Maybe I should comment on why I'm picking the future cone and not the past cone. All in all, why not? And this is, everything is symmetric up to the point where you want to understand who is your one-dimensional guy. And the one-dimensional guy, if you go to the past to the past cone, then the one-dimensional guy would be something like minus infinity 0. But that is not really a field of scale. It's not stable by product internal product. So minus times minus is positive. That's really kind of basic math. But it helps me in selecting, so it breaks a little bit the symmetry. So when you take the internal product, there is a sign that does better than the other. So you need really to go up. And last but again, not least, all in all, this is in line with the realistic point of view. So we know from Einstein that we can only move forward. So we lack of okay. So if you have no better idea, maybe follow what Einstein said. It's not. No. All right. So now let me go. I totally forgot 15 minutes, more or less.
We have 30 minutes.
30. Okay. With all this said, let me throw a couple of
30.
30. That's a lot. I will conclude it.
20 something.
It's okay. You can okay. We go to lunch early. Let me start with some basic taxonomy. Let me try to throw on the table a few definitions. So first of all, let's say that a pre-wedge is just like a vector space, but I can only multiply by non-negative reals. So by this definition in particular, a vector space is a pre-wedge. But I want to exclude this immediately because once I have a pre-wedge, once I have this sort of structure, I can define a partial order. I can say that V is less than W if for some Z, B plus Z is W. Okay, and now a wedge is a pre-wedge, so this is a partial order. So vector space is, in a vector space, everything would be less or equal than everything else. While in here, I impose some anti-symmetry. And I also impose something which does not come for free from the definition. I want some, relation between this partial order and multiplication by coordinates. So any vector should be the sup of, alpha times V for alpha smaller than 1. It's not that much to ask, but you need that, otherwise a few things go very well. So that's the basic algebraic structure. Let's say the hyperbolic norm is just a map from the wedge to say 0 plus infinity. I want to keep plus infinity inside because that's what happens in examples, and which is one homogeneous and satisfy the reverse triangle. Okay, and now when I have two wedges, which kind of maps of continuous maps I'm interested in? Well, I want to study linear maps with this monotone convergence property. And once I have such a map, I can define the operator norm of a map, as in the first slide. I define the operator norm of L is the inf of norm of LB in the target space among all the V in the source space with norm LB. This turns out is an hyperbolic norm on the wedge of linear maps. Okay. Now, in this business, the fields of scalar, or if you want, the simplest non-zero wedge would be 0 plus infinity included, and the dual of a wedge would be the space of morphisms with values in this guy. Not much like the dual of a Banach space is the space of morphisms into R. The dual of a module is the space of module morphisms into the basic ring, etc., etc. So this very much the same. Of course, this is not a field in any usual sense, but let me pretend that. Now, here are some examples. So, first and foremost, LP spaces. So LP spaces for P is more than one, possibly negative, fit very well within this framework. Of course, LP spaces, classical intended LP spaces, they do not work well. We don't have any triangular inequality for the normal classical intended. But in fact, what I'm suggesting here is that, maybe we should be fine with that. We should not insist in having the classical triangular inequality for the LP norm for P more than one. Maybe we should be happy to work with the reverse triangular inequality. And the definition is this. Suppose you start with a sigma finite measure space, and you take, let's take the collection of all 0 plus infinity valued measurable function up to equivalency. after quality almost everything. And for any such function, well, first of all, as a first easy fact to check, well, this is a wedge, and this is self-dual. Okay, so the dual, so it is rather, let me notice the following. So for any f in this guy, in this L of x, I can define a linear map from L of x to plus infinity. Let me call this guy Lf of g. This is the same that is in our standard theory, just the integral of FGBN. Okay. Notice that given that I'm assuming that f and g are non-negative, this integral is always well defined, possibly plus infinity, but it's always well defined. Okay, so I don't need to insist on any integrability properties. And Beppo-Levi tells me that this map has the monotone convergence property. And in fact, in some sense, this is the only kind of continuity property that I can imagine for this sort of map, especially if I'm not insisting in a setting where I'm not insisting on working with LP function classically. Okay, so a relevant part of the reason why I'm working with this monotone convergence properties, because that's basically the only continuity property that I'm able to find for this sort of function. Okay, and not only that, but every linear map from this guy to 0 plus infinity with the monotone convergence property is of this form. It is exercise. So in this sense, it's a self-dual wedge. Okay, and now on this wedge, I define the LP norm as this, and I can wonder what is now the dual of the LP norm in this setting, and it turns out that is the DLQ norm, where 1 over p plus 1 over q is equal to 1. Now here, you notice that if p is positive, it's between 0 and 1, then q is going to be negative. So the conjugate of say 1/2, if p is 1/2, then q is minus 1. Okay. Let me maybe try to say a couple of things more, because you can, of course, think, oh, hold on a second, this is complete nonsense. Why, for instance, why do you insist of taking the same space for any p? That's not what we do in standard LP spaces. And why do you insist on maps with waves actually plus infinity? Why are you doing all of this? And let me point out the following. One could say, look, let me try to define LP as the collection of functions, from x to r, let's say, such that the integral of absolute value of x to the power p is finite. That would be another certainly an option that is on the table. And now let me observe, say that our space is 0, 1 with the vector. So let me take the function f identically 1 that belongs, of course, to each of these spaces to the power of 1 interval, and let's see which sort of function it induces on LP through that extremely natural form. That I mean, don't expect an objection in some sense of this. So this, of course, if f is 1, g is just the integral of g. And now here's the problem. If g is a function in LP in this sense, this makes no sense. Because this is like knowing that, if I know that the square root of g is integrable, why should I know that g is integrable itself? That's, the function is 1 is not necessarily linear 2. So the very definition of what is a linear map is that falls off. And not only that, now if you say, okay, so decide just to work with a negative function, then very easily this extremely natural map and just integrating against 1 takes the value plus infinity. So I must be ready to work with linear maps with values in plus 1. Okay, and this the duality relation that I'm pointing this out is just the fact that it's a little bit more of the fact that you have the reverse Hölder inequality is in place here. For P and Q, such that 1 over P plus 1 over Q is equal to 1, you do have this inequality, and for given G, you can saturate this inequality if you play smartly with that. Okay, the proof of this is as trivial as the proof of the standard. Basically, the function 1 over p z to the p is concave, and its concave dual is 1 over q plus z to the q. So that's a first example that pops out. Another example is the following: we can take a Banach space, multiply it by r, and look at the future cone in there. Much like if we start from R3, we multiply by R and we take the future cone we get, or basically our future cone in Minkowski, we can do this on any Banach space. And I can endowed it with the Lorentzian norm, which is square root of t squared minus norm squared. You can check that this satisfies the reverse triangle inequality. And a little bit interesting, you can take, now this is a wedge, this is an hyperbolic norm. I can take the dual of this wedge in the sense of morphisms with the MCP, and the dual of this guy is canonically isomorphic at the future cone in the dual of the Banach space, where this dual is the classically intended Banach space dual. So in some sense, a very natural relation in between the classically intended continuous function, in the sense of continuous and bounded, pops out in relation to this MCP property of functions in the future. And also because of this fact, some of the results in this hyperbolic Banach spaces setting can also be read through the lenses of classical Banach space theory. Maybe also let me mention this. This guy comes with a topology, classical, the Euclidean topology times the topology of B, and this guy is locally compact, or if you want, globally hyperbolic, if and only if your Banach space is finite dimensional. And this guy is directed complete, at least locally, if and only if this is complete in the classical setting. So if you start with a normal space and you play this game and you want to know whether directed set, bounded directed set have a supremum in here, well, this is always true if and only if your original known space is complete in the classical sense. So there is a further relation between classical completion and this directed completion. And last, Ri's theorem can be read even through the eyes of this kind of structure that I'm trying to paint. Of course, we know that they do, say, if I have, say, a compact out of space, and I take the dual of continuous function, it is isomorphic, isometrically isomorphic to the space of Radon measures. We can try to do the same game here. We can take, say, a Polish space and take the collection of lower semi-continuous, non-negative lower semi-continuous functions. So one-sided continuity is a wedge, okay? And there is a natural hyperbolic norm of this wedge, which is just take the inf of f, so not the soup of the absolute value, but just take the inf. For trivial reason, this satisfies the reverse triangle inequality. And you ask yourself, well, what are those linear functionals with values in 0 plus infinity that satisfy the monoconvergence property? And for trivial reasons, this is way trivial, it's more trivial than the classical Ri's theorem. This is just a space of measures. So with the total ratio, with the total mass. So in some sense, what I'm saying, one of the things that I'm saying is that mu of x is equal. So let me say this: the is the equal of the inf of the integral of f d mu among all the functions f that are greater or equal than 1 everywhere. I can pick f equal 1 and I get mu of x for non-negative measures and. So the monotone convergence property is what gives you, the kind of continuity that is needed to get. I'm not being extremely precise, especially for rho constants measured with infinite mass, but I don't want to be precise. I just want to convey some. All right. Now there is one further thing that I want to discuss, which is the following. I discussed and tried to convince you about the usefulness of the directed completion procedure. Then I added some algebra. So what I could do, I could start from a wedge, complete it in the abstract sense, and maybe I still want to have a wedge in my end, possibly a complete wedge. No? So that's this. I mean, it's so basic that we don't think about this when we work in Banach space. But if we start from a non-complete normal space and we complete it, of course, the completion still carries the natural structure of vector space, because basically the sum is continuous with respect to the distance coming from that. And one should check whether the same is true in this setting, and it is. Although it is a little bit less non-trivial and worth to be commented on. So the point is that basically, so what's our rule for extending? What's our notion of continuity is the MCP. So the kind of question that we have is the following: is it true that, say, if I have, for instance, a directed set A, and I have a vector, in my wedge, and the directed set has a supremum, is it true that the supremum of my set plus this vector is the same as the supremum of, the set plus this vector, so the collection of all W plus V as W varies in A. And the same question you can ask, of course, with a product by a scalar. And when you try to do this, there is one inequality which is trivial. Now for the product formula, once you have one inequality, you also get the other one by multiplying basically by alpha minus 1. And in your dreams, you would like to do the same. You have one inequality, and then you apply the same by adding minus b. Except that this is precisely the thing that you cannot do. And I insist that you cannot do this because, for instance, these empty spaces, that's plus infinity is really within the gate, since everything is not negative. Okay? So in particular, whereas there is an analogous formula for the inf for the product by scalar, the analogous formula for the sum, I mean, I've not been able to do it. I don't think is there. I don't know how to get it. And the actual, to prove this, what is needed is a weak version of the cancellation property. So again, in a natural vector space setting, when you have ordered vector spaces, you always have this sort of property. If A plus B is less bigger than B plus B, then by adding minus B to both sides, it would imply that A is less bigger than B. In this world, this is not the case. Imagine, what was the question? No. Imagine your wedge is 0 plus infinity, and B is precisely plus infinity. So 2 plus infinity is less or equal. In fact, it's equal to 1 plus infinity, but certainly 2 is not less or equal. Okay. But still, what is true, what is there is a weak version of the cancellation property. So you can cancel most of this guy that you added. So A plus B less equal than B plus B implies that A plus half of B is less equal than B plus half of B. This is still true. And of course, if you continue, you can basically remove most of the B, and then that's sufficient for your proof. And why is this true? Well, I mean, it's a basic algebra thing. So basically, A plus 1/2 of B, you write it as half of A plus 1/2 A plus B. But now you know that A plus B is less or equal than B plus B. Okay? So now you rewrite this as 1/2 B plus just half A plus B. You try again the fact that A plus B is less equal than B. Okay. And it doesn't matter if you follow this simple proof or not. But the point is that this does not hold, but we have a weak version, but strong enough to get it. And to be honest, this was the first surprise, the first honest surprise that I got when studying this business. I was not prepared for this. I was a little bit scared about this completion procedure. But here I did nothing. So you can define, you can forget whatever I did, up to 1 minute ago. The division wedge, I mean, you can throw it there, and it naturally, by itself, it possesses this MCP property without enforcing it. So, which is, I think, it's a cute thing. So you can copy the wedge and get a wedge structure on the convection. There should be more to be said, but lack of time, I will not say. Stop here for this. Now, what about extensor linear maps? Of course, the first, result we have in function analysis is a Banach theorem. We can extend linear maps. We all know this. And there is a version for wedges, which is formally the same, except you just basically exchange inequalities. So if you have a wedge, you have a function which you can imagine to be your hyperbolic norm, so something which is super additive, not subadditive. And you have a subspace, and you have a linear map which is bounded from below by this other, hyperbolic norm, if you want, on the subwedge. But then the point is that you can extend this to the whole original wedge without, by still satisfying this, so without destroying this one. Loosely said, but that's the essence of this. I want to say a couple of things. So the proof, the structure of the proof is the same as the classical Banach. You just have to prove that by its own lemma, you just have to prove that if W prime is not already the full W, you extend it by adding 1 point, and you have just to be sure that you can extend it by still satisfying this. But the fact that the fact that plus infinity is a guy that is actually, and you don't have cancellation property, may complicate things quite a lot. Now, of course, you can say, okay, hold on a second, but if I extend it by putting plus infinity on a new point, then this is going to be surely satisfied. And that is true, except you can, you have to be a little bit careful, even more than a bit, in fact, because, a situation you can easily run into is the following, say you have your wedge, this is your wedge, this is your original subwedge, you extend your linear map in this point by putting, say, plus infinity, but now if on this original wedge the map was finite, now there is no further extension that does the job, because how can you define, the value of the map here in such a way that the average is going to coincide with what you had before? If this is plus infinity, whatever you put in here, there is going to be plus infinity, but maybe here the value of the function was the same, whatever, not plus infinity. So you have to pay attention. In fact, anyway, whatever you put in here, in there, you cannot go below 0. So there is some attention to be paid. So it's a bit more complicated, but the structure is the same. And one remarkable thing is that so there is one reason to be happy about this theorem and one reason to be unhappy. The reason to be happy is that this implies the classical humbug. So you pick your vector space, your subadditive map, and you can cook out the future code. Basically, you can take the collection of couples RV such that T is greater than PD. This has the subspace induces a subwedge in another way, and you can take here as Q map, the map identically 0, and as linear map defined on the subwedge, just the T variable minus L of V. Then this inequality is telling precisely that T is non-negative on the subwedge. And the theorem is telling that you can extend T to be non-negative on the full original wedge, which, if you read what this means, it means precisely that L of V is going to be less bigger than P of V everywhere. Which, okay, that's I think it's nice. Sure, this is notable. But the bad thing, the terrible thing, is that is a continuity issue. So Banach, when you pick, when you extend something which is non-bounded, the extension is going to be non-bounded and therefore continuous. Whereas in this setting, being bounded from below by, say, the hyperbolic norm implies nothing about the MCP property of T. So while the classical Banach allows us to extend continuous operator into continuous operator, this, if you do it blindly, you might end up with an extension that does not satisfy the MCP. Okay, does not have, so it's not continuous in the classical sense. So the theorem looks useless in some sense, because continuity, of course, we want to keep continuity. And this links to the following couple of comments. So the first one, which is either scary or fascinating result, depending on whether you feel adventurous or not, but the MCP property cannot be quantified. So the continuity, of course, can. That's what we always do in function analysis. Actually, the first result in function analysis is that a linear function is continuous if and only if it's bounded. So that's good. There's nothing like this. There is nothing like this in this world. The good old epsilon delta theorem. Forget about that. So epsilon delta is Cauchy's realm. This is not Cauchy's realm. This is Dedekind realm. So you cannot quantify. You cannot quantify continuity. Still, so I was a little bit concerned about this, but still, it seems that at least for what concerns, so there is still room for epsilon delta kind of argument, quantitative rigidity results. So in particular, I think I can now say that we do have a proof of the almost splitting for sectional time-like lower sectional bounds in the Lorentzian setting. This is the first quantitative result that I'm aware of in Lorentzian signature. It was in sectional. There are scary voices, scary rumors around. Can I? Okay. So Andrea told me yesterday that they should have him, Clemens Seman, and Vanessa. That's her name of Vanessa? Friborts. Thank you. They should have a counterexample to the Narus result for lower Ricci bounds. So the question of whether we can develop a Seeger coding theory during the signature is, very much okay. But still, so in this framework, at least some epsilon delta is still there, despite the fact that MCP cannot be quantified. And so how do we resolve this problem? Well, in fact, if the source wedge has some property that is satisfied in all the examples that I know of, then there is a natural way of, in a sense, replacing your map with the linear map, which might not have the MCP, with the one that does that. Loosely speaking, so this property is a property of the wedge that better links sum and suprema. In some sense, it does the following. Suppose you have a sequence, an increasing sequence that has a supremum x, and suppose that x is y plus z, then maybe you will want to find increasing sequences converging to y and z, converging to supremum, so that every time xn is equal to yn plus z. This is a property that is not always true. whenever it is true this for directed set in the proper way, you can do this replacement of linear maps to the map with MCP. Otherwise, I don't know what to do. But this is a property that emerges and is very naturally satisfied by all known examples. Okay, couple of 2 minutes. Okay. Then okay, what's the natural complete class of objects? Well, the natural one is is a cone, so a wedge, which is also directed complete, where supreme directed set exists. And there is also, much like in the theory of ordered vector spaces, complete lattices also play a role. So a cone, which is also a complete lattice, so super inf exists, and the inf behaves well with the sum, deserves a special name, and calling them cone with joints. And there is and in this setting, this complete setting, there is a quite nice thing that you can do. You can isolate for any element of a cone. You can isolate what it is, in some sense, its path at infinity, because the collection, so fix V, and observe that the collection of W, which are less or equal than alpha V for any strictly positive alpha, this is a collection which is closed by sum. If I pick W1, W2 in here, for trivial reason, W1 plus W2 is still in here. Being closed by sum, it means that this set is directed in particular, because the sum of two vectors is bigger than either one of the two. So there is a supremum of this set by definition of directed completion. And this supremum, we can call it epsilon V. It's what remains of epsilon of V when we multiply it by very, very small number. And in cone joints, the cancellation property takes this particular nice form, which is useful in applications, particularly the Banach theorem extension theorem that discussed works not just for functions with value in 0 plus infinity, but really in cone with joints. And this kind of cancellation property plays a crucial role. And also plays a crucial role in the proof of the of Baire theorem in this setting. So again, we all know what the classical Baire theorem is, but let me, I want to conclude with the following remark. Well, first of all, there is a version of Baire theorem in the context of cones with joints. I never really discussed. I discussed the MCP, but I never really discussed the topology to be put in this sort of spaces. And the reason is I don't know which topology to put. That in general is an issue in the context of Lorentzian pre-length spaces and this metric space-time to understand the relation between the time separation, the measure, and the topology. I don't think the picture is fully clear. And in particular, there is no nice topology nice enough for which the continuous map are precisely those with the MCP. I mean, the Scott topology is not Hausdorff. I'm an analyst. I don't want to. Topology, at least not yet. I'm not ready. And a remark that I want to make about Baire theory is that well, let me actually state this here. So suppose you have a partial order, and suppose you have a topology on it, which satisfies the following two properties. The first property is that whenever you have an open set, this open set contains a diamond, in the sense of order intervals, with non-empty tau interior. Okay? And the second property is a kind of completeness property. So whenever I have a sequence of nested diamonds, there should be some common point belonging to all of this. This, of course, reminds the classical assumptions in Baire theorem, where the topology typically is induced by the given distance, and any open set contains a closed ball with non-empty interior, and we have a Cauchy complete. So this replaces the ball things, and this replaces the completion. But the interesting fact is that the kind of limit that is taken in the completion property might have nothing to do with the topological limit. I'm saying nothing about the tau relation between AN, BN, and C. And you can also phrase the classical Baire theorem with the same proof by just think about a complete metric space and a topology for which you have this open and closed condition, I mean, both inside with an interior. And still the conclusion is that if you have a sequence of tau dense and tau open sets, well, then their intersection is tau dense and open. So this is yet another, if you want, existence result. So a set is dense, in particular is not empty. So it's an existence result in this setting. The tree mirrors the classical one. And much like for Banach, this implies the classical version, because if you start with a complete metric space, you multiply it by R and you equip the product with the causal order like you would do in Minkowski starting from R3. Then it's a triviality to check that if you know this, you also get the classical version. So it's a new point of view on the classical bed property, but it stands by itself in this field. And that's all I wanted to say. Thank you for this.
No questions? So, what about defining gradients or things like that?
Yes, that's that's the next step. In fact, the reason why Internet this is introduced is to try to define the gradients and differentials. I'm working on this together with Romano Link. I mean, here is a student of mine. We are working, so I'm not ready to make any claim. I'm optimistic, but that's what I think we should be able to do some cotangent business together with some closed operator in some sense, bringing causal function to their differentials. But the extent, I mean, incidentally, the question is never whether you can define things, but whether the object you define will actually be useful to prove theorems, right? And in that regard, time will tell. So I'm optimistic again. That's why I'm working, but it's too early to tell. So, but that is certainly the main direction I want to take.
Any other question? Yes, thank you.